Hey guys, welcome to a new video. In the last class, we wrote a program to solve an auto cycle and we were able to plot the state points. And I also mentioned that in order to connect the state points, we need more information. So today we are going to be writing a program that actually solves the piston kinematics equations. So piston kinematics basically tells us how the piston actually moves from top dead center to bottom dead center, and in this process how does the combustion chamber volume change as a function of the crank angle. All right, so to do that we are going to start writing a simple program. I'm going to start with clear all, close all and CLC, and then I'm going to assume the geometric parameters of my engine as 0.1 meters for bore, stroke is going to be 0.1, and connecting rod length is going to be 0.15, and for compression ratio let us go with 12. Okay, so the first thing we need to do is compute the swept volume and clearance volume, which we have already done before. So the swept volume is going to be pi by 4 multiplied by bore square times stroke. Okay, and the clearance volume is going to be equal to the swept volume divided by the compression ratio minus 1. Okay, so now let us save this program and we'll just call this as engine kinematics, and if I hit F5, the program runs and VC and VS have been computed. Great. So what we are going to do is we are going to use this particular formula that determines how the volume inside an engine combustion chamber is going to change. This was derived from purely geometric relationships. Now let us say that your crank angle theta is 0 degrees, which means that's going to be your top dead center. So what I'm going to be doing is I'm going to be coding this relationship for a particular value for theta. So I'm going to say that theta is equal to 0. And then since the equation is pretty large, I'm going to break it up into several terms. So the first term that I have is term 1, which is 0.5 times the compression ratio minus 1. Okay, so that's going to be my first term. My second term is going to be r plus 1 minus cos d of theta. And my third term is going to be r square minus sine d of theta, the whole square, and this entire thing needs to be given a power of 0.5. All right, so finally my volume trace is going to be equal to 1 plus term 1 multiplied by term 2 minus term 3. Now this entire thing needs to be multiplied by the clearance volume V underscore C. So we clearly have some new terms here. So what is R? So R is nothing but the ratio of your connecting rod length to the crank pin radius. And your crank pin radius is nothing but the stroke divided by 2. So now when we execute this code, we get this error saying that undefined function or variable RC. So RC is our compression ratio. Since we are using the variable CR, I'm just going to convert this into CR, and now if I execute the program, you can see that it works. A simple test that you can perform to make sure that the code works correctly is when theta is set to 0, then the volume should correspond to the clearance volume, which is basically your top dead center volume. You can see that your clearance volume and your capital V are exactly the same. And what you can do is you can put theta as 180, and when you execute the code, you can see that this particular volume is going to be the sum of clearance volume and swept volume. In other words, if you basically do Vs plus Vc, that is exactly equal to 8.568 E minus 4. So we know that our code works correctly. Now, the whole idea behind using this formula is because it can actually provide a lot of benefit. So what I can actually do is I can say that theta is going to be length space 0 to 180, and I can pick 180 values. So basically I'm creating an array of theta. And then here, what I can just do is I can just use the element wise operator here. And where else do I need it? I think that's it. Well, I might need it here. And if I put a semicolon here and if I execute the code, okay, looks like there is an error. I missed the element wise operator here. Now if I execute the code, you can see that now volume is an array. What I can do is I can plot theta and v, and that's it. This is how the volume inside your engine is going to vary. So now if you have been assuming that the volume actually changes linearly between the top dead center and bottom dead center, you are wrong. This is how the profile changes, and our code is quite generic. What I can actually do is I can plot my volume, or sorry, theta versus volume, and maybe just increase the line width a little bit so that you can all see it, right? And here instead of 180, if I put 720, and if I say that we are going to be using 720 values, there you go. So now we have calculated how the volume trace is going to look for 2 cycles, right? That's pretty neat, right? So we are going to be using this particular program to get the volume information during the compression and expansion stroke. Once we do that, we will be able to complete our PV diagram correctly. In order for us to use this particular program inside our auto cycle program, we need to basically be able to call this particular program. And that is where we use a concept of functions. Now what I can do is I can just copy this entire code and I can paste it in this particular program and make it work. But then that's going to be a bit ugly and it's going to be very hard to manage your entire program. So what we are going to do is we are going to convert this into a function. So a function is nothing but a piece of code that you can reuse by just calling its name and passing in the right parameters. So let me actually first demonstrate this process and then kind of explain why it is useful. So what I can do is I can use the word function, and it's going to have a particular output, which in this case is the volume trace. And I'm going to say that the function name is engine kinematics. And the input that it's going to take is bore, stroke, connecting rod length, compression ratio. What else do we need? Well, we need a starting crank angle and an ending crank angle. I'll explain to you what that is. So here the start refers to, maybe what I'm going to do is just add starting crank angle and ending crank angle, right? Something like that. And I'm going to replace this guy with start crank and this guy with end crank. All right. So what we are basically doing is we are creating a template, right? So this is a code template, and the name for the template is engine kinematics. So whenever we want to substitute different values, we just call this function and we pass in the right values. Let me explain that. So here the first thing I need to do is delete these 3 lines. Why am I deleting these 3 lines? Well, I'm going to be inputting the value for bore, stroke, and connecting rod when I call the function. All right. Again, what does call the function mean? We will look into it right away. So I'm going to delete, these 4 lines. And then for a function, we need to have an end keyword. And I'm going to remove this plot command as well. Save this. And then if I go to command line now, what I can do is I can type in engine kinematics. And then I'm going to pass in the input values for bore, stroke, connecting rod length. I think we put in 0.15, compression ratio maybe 12, starting crank angle 0, and ending crank angle maybe 180, right? So I can do this and I can close this, and I'm going to say that the results from this is going to be stored in a variable called v compression. All right. So if I execute this code, before I execute, I think there's a small typo here. So this is con rod, whereas this is con rod. So I need to delete this guy. And if I execute this, you can see that my volume trace is printed out. That's it. Now what I can also do is I can plot V compression, right? And if I open this guy up, okay, looks like there is some problem. It looks like our compression array just contains 1 value. We need to figure out why that is. I know the mistake that I made. So in my linspace command, I put in the wrong parameters. So I need to have start crank, end crank, and then maybe 100 values. So now if we save this function and then do this again and then plot V compression. There we go. We can see our volume trace. And almost immediately what I can do is I can go back here and then just call this as 720. And I can plot my compression again, and that's it. So a function is a very nice way to basically reuse code. Let's talk about some syntax. So we need to have this function keyword. Matlab requires it. Now you can see that here I have a square bracket, right? This is basically an array. What I'm doing is I'm creating an output array. And in fact, I can just do this since there's just only one output. I can save this and I can just run my code again. And if I plot it again, you will see that I'm getting the same result. So this right here is an output, but ideally what I want is I want you to get into the practice of having this square bracket, because in Matlab everything is an array. So we have this output array which contains our volume trace. Now remember that the way Matlab knows that this is the output is because we are calculating V here. If I rename this variable to volume trace, and if I save the program, and then if I run the code, you will see that I'm getting an error saying that output argument V is not assigned. So there are two choices. I can either call this as volume trace, and then now if I execute the program, it's going to run. Or what I can do is I can just give it a simple name V, and simple name V, and the same name here. And then if I run the code, it's going to work correctly. All right. So this is what you call as a function definition, because we are defining what the function is. And this right here is the name of the function. Now remember that the name of the function and the name of the file should exactly be the same. Now these right here are the inputs to your function. Now here I have bore, stroke, connecting rod length, compression ratio, crank, starting crank and ending crank. And when I call the function, so this right here is what you refer to as calling a function. So calling a function means using the function, using the template with the appropriate values. Now you need to remember that the order in which you pass the inputs is very important. You need to make sure that the number of inputs that you provide match and the order of inputs also match. So for example, let us say that you accidentally forget to input the last value. It's going to basically say that there is an error in this particular line number 12. It says that theta equal to lin space start crank and end crank, not enough input arguments. Now we know that in this case the end crank was not defined because we deleted that input. So you need to be very careful that you provide the required number of inputs in order to evaluate the function correctly. All right, so here I'm just going to put semicolon so that there's no output from this function. Now what I can do is I can go back to my auto cycle, and then what I can do is I can just paste this line of code right here. I can say that V compression is engine kinematics, and what we need to do is we need to specify the bore, the stroke, the con rod, compression ratio. Now for compression, the starting crank angle is 0 and ending crank angle is 180. That's it. Now what about bore and stroke? Well, we have already defined bore, stroke and connecting rod here. So now if we run the program, you can see that it runs correctly. We are still getting the incorrect PV diagram. But if I type in V compression here, you can see that its value is getting printed. That's amazing. So now what are we going to do? Well, if you remember, PV power gamma is a constant, correct? So along the isentropic process, pressure times volume, power gamma is going to be a constant. So what I'm going to do is, I'm going to first determine our constant C, which is basically the right hand side, which is nothing but P1 V1 whole power gamma, right? So if I determine this constant, then I can say that during my isentropic process, P times V compression power gamma is equal to constant, right? So what I can do is I can say P compression multiplied by V compression power gamma is equal to this constant C, correct? Now this guy right here is known, V compression is known, which means I can actually compute this guy by taking this V compression power gamma And all I need to do is divide my constant C by that particular term. Now since V compression is an array, I need to use the element-wise operator. So we have an error. We need to make sure that we put a dot here as well. So we have P compression, V and V compression. So what I can actually do is I can go to my first plot and I can plot V compression, and I need to use capital, and P compression. And if I execute the code, there we go. You can see that I have my compression curve. It's pretty amazing, right? Now I can follow the same process for the expansion process also. We can just copy this entire code, paste it here. Actually, we should not paste it here. Maybe we should just paste it after P3 and V3 have been determined, and I can just paste it here. And I can say that this new constant is actually P3 times V3, correct? And we are going to calculate V expansion. And the only difference is this time the number is going to be from 180 to 360, right? Because you want the volume to represent your expansion stroke. Oh, actually we made a small mistake here. So the volume here should be the expansion stroke, which means this should be 0 to 180. Whereas this guy, since it's compression, it should be 180 to 0, because during your compression, your volume should reduce. It should not increase. All right. So we do that, and which means here we just need to change P expansion. And then instead of compression here, I'm just going to call it expansion. Okay, so that looks good. So we finally need to go here, copy this guy, and instead of compression, we just put expansion. Now, if you look at the output, you can see that we have this nice looking compression and expansion curves. And this curve is the right way to connect state 1 and state 2. If I compare this with our second graph, maybe I should just run the program again, right? So you can see that in both of these plots, the state points are exactly the same, but on the right hand side, we have the wrong connections, which means the area under this curve and the area under this curve are completely different. And this is the right way to do it. Now, as far as your assignment is concerned, I'm going to let you figure out how to connect states 2 and 3 and states 4 and 1. That's going to be relatively simple because that's just going to be a straight line. I hope you figure it out, and I'll see you guys in the next video. Bye.